You remember yesterday. You do not remember tomorrow. Ludwig Boltzmann understood why, and the answer destroyed him. On a family holiday in Duino, Italy in 1906, he hanged himself while his wife and daughter waited nearby. His entropy equations still dismissed by colleagues who refused to believe atoms were real. A century later, we know he was right about everything. The direction of time is not written into the laws of physics, and it turns out to be an accident of the Big Bang. Once you understand this, your morning coffee becomes a window into the first moment of creation, and you cannot think about time the same way again. A question has troubled physicists since Boltzmann's era, and it starts with something strange about equations. The fundamental laws of physics work equally well forwards and backwards in time. Show someone a film of two billiard balls colliding, then show them the same film in reverse, and both versions obey Newton's laws perfectly. Nothing in the mathematics distinguishes past from future. Yet you have never seen a broken cup gather itself from the floor, leap onto the table, and reassemble into a perfect vessel. Cream does not spontaneously unmix from coffee, separating into a white blob floating in black liquid. Dead people do not come back to life. The laws permit all of this, and the mathematics allows it, because every collision and every chemical reaction that makes up these processes can run backwards without violating a single equation. Joseph Loschmidt threw this contradiction in Boltzmann's face in 1876, and physicists now call it Loschmidt's paradox. If the microscopic laws are reversible, why is the macroscopic world so obviously not? During my years holding Newton's chair at Cambridge, the Lucasian professorship, I returned to this puzzle again and again. A brief history of time explored these ideas, though even then I did not fully understand all the implications. What makes this problem so important is that it connects to everything, including why you exist at all. Your smartphone battery offers a window into this mystery. Charging it forces lithium ions into an ordered arrangement, a state of low entropy. Using the phone scatters those ions through the battery's structure, increasing entropy with every text, every video, every notification that lights up your screen. The second law of thermodynamics claims it's due each time. Batteries die for the same reason everything dies, and the principle governing your phone also governs the fate of the universe. James Clerk Maxwell once imagined a tiny demon who could sort fast molecules from slow ones, seemingly decreasing entropy through intelligence alone. Open a small door for the fast molecules, close it for the slow ones, and heat would flow from cold to hot, violating the second law. Boltzmann showed why even the demon fails. Observing molecules requires information, and information carries thermodynamic cost. The demon pays in entropy what it saves in temperature difference, which means the second law survives. Rudolf Clausius named this quantity entropy in 1865, and the best way to think of it is as a count of arrangements. Entropy measures how many ways you can arrange the microscopic components of a system while keeping its overall appearance the same. Boltzmann made this mathematically precise with his famous equation, S equals K log W, where entropy S is proportional to the logarithm of W, the number of possible microscopic arrangements. Vienna's Zentralfriedhof Cemetery displays this equation on his tombstone, though Boltzmann never lived to see his vindication. Squeeze all the gas into one half of a box, and relatively few molecular arrangements maintain that configuration. Let the gas spread throughout the entire box, and vastly more arrangements become possible. The number grows so large it makes all the stars in the observable universe seem small by comparison. The second law of thermodynamics states that entropy tends to increase, which means things evolve from less probable states to more probable ones. A broken cup on the floor is more probable than an intact cup on the table because scattered, shattered pieces have far more possible arrangements than atoms organized in one specific cup shape. Cream mixes with coffee because mixed states overwhelmingly outnumber separated states. Decades passed before anyone recognized the next connection. Claude Shannon, working at Bell Labs in 1948, discovered that information obeys the same mathematics while trying to solve a practical problem about sending messages through noisy telephone lines. What he found ran deeper than engineering. The entropy in physics and the entropy in information theory turned out to be identical, and this discovery laid the foundation for smartphones, the internet, and artificial intelligence. Erasing a file on your computer is not just manipulating bits. You are participating in thermodynamics, because the universe processes information in only one direction. Modern supercomputers running large language models generate enough heat to warm buildings. Artificial intelligence carries real thermodynamic expense, and every answer these systems produce, every image they generate, every conversation they hold, costs the universe entropy. The same laws governing your coffee cup govern servers humming in data centers around the world. The universe resembles a vast jigsaw puzzle that started with pieces arranged in a very particular way. Physical processes have been shaking and jumbling those pieces ever since. Every interaction, every collision, every chemical reaction adds another shake to the cosmic box, and the puzzle moves relentlessly toward more probable, more disordered states. Notice something important here. Saying entropy tends to increase gives us a direction which physicists call the thermodynamic arrow of time. This arrow always points the same way for every process we observe, from boiling water to burning stars to living and dying. And here is where it becomes strange. The thermodynamic arrow seems to explain why cups break but do not unbreak, why we age but do not grow younger, why ice melts in warm rooms. But it raises an even deeper question. For entropy to increase, it must have been lower before, and tracing this backwards forces a conclusion. The universe began in an extraordinarily special, low-entropy state. Sean Carroll calls this the past hypothesis, and we do not derive it from physics. We assume it, and that assumption carries the weight of everything. The Big Bang was not a chaotic explosion scattering matter randomly. The opposite happened. The early universe existed in a state of remarkable smoothness and order. The Kobe satellite first detected the cosmic microwave background, that faint glow from the early universe, and the Planck mission later mapped it with extraordinary precision. Matter was distributed almost perfectly uniformly, with density variations of only about 1 part in 100,000. From that incredibly ordered beginning, everything has been running downhill. Stars form, burn, and die. Galaxies cluster and eventually disperse. Black holes grow. All of these processes increase entropy, and the arrow of time points away from that special beginning. Black holes deserve attention here. Physicists once thought black holes might violate the second law, because throwing something into a black hole makes it disappear from our universe. If its entropy vanishes, the total entropy of the universe could decrease, which would violate the law. Jacob Bekenstein, then a graduate student at Princeton, first suggested that black holes themselves carry entropy. My initial reaction was disagreement, and I felt certain I could prove him wrong. Working with Roger Penrose, who would later win the Nobel Prize for his work on singularities, I had already shown that singularities were inevitable in gravitational collapse. Black holes seemed like simple objects to me, characterized only by mass, charge, and spin. Entropy looked like an unnecessary complication. I was wrong. Trying to disprove Bekenstein ended up proving him right, and the process revealed something even stranger. Black holes carry enormous entropy, proportional to the area of their event horizon, the surface beyond which nothing escapes. Matter falling into a black hole adds its entropy to the hole itself, rather than losing it. The second law survives, but now it applies to ordinary entropy plus black hole entropy together. This discovery taught me something about certainty, because the most confident physicists are often the most wrong. Bekenstein was right, and my failure led somewhere important. Black holes are not cold, dead objects. They have temperature, and they radiate energy in what colleagues now call Hawking radiation. The process happens slowly, almost imperceptibly, but black holes radiate. Given enough time, even black holes evaporate away, returning their entropy to the universe in a different form. The arrow of time operates even for black holes. What remains unexplained is why the beginning was special. The laws of physics themselves offer no answer, because the laws work equally well forwards and backwards. They do not prefer low entropy over high entropy. Something else determines the boundary conditions, the initial state of the universe. Another arrow of time exists, the one you experience most directly. Psychologists call it the psychological arrow. You remember the past but not the future, recalling what you had for breakfast this morning while having no access to what you will eat tomorrow. This seems so fundamental that imagining it otherwise feels impossible. But a physical reason exists for why memory works in only one direction. Memory is a physical process. Remembering something means a record of that event is encoded in the structure of your brain, and creating such a record requires energy. It creates heat and increases entropy. The act of remembering, of correlating your brain state with past events, only works in the direction of increasing entropy. Forming memories of the future would require entropy to decrease, which contradicts the thermodynamic arrow. Rolf Landauer, working at IBM in 1961, proved something that changed how we understand computation. Erasing one bit of information in any physical system, whether a brain or a computer or anything else, must release a minimum amount of heat. Technology cannot overcome this limitation because it is a fundamental law, now called Landauer's principle. Your memories exist because the universe pays the thermodynamic price for storing them, and every thought you have, every recollection, generates heat that dissipates into your surroundings. You are literally warming the universe by remembering. The connection runs deep. Your experience of time flowing from past to future is not separate from the thermodynamic arrow. It is a consequence of it. You remember the direction in which entropy increases because memory formation itself increases entropy. If entropy ran the other way, your perception of time would reverse with it, but you would not notice the difference because your memories would also reverse. Your entire experience of time rests on this foundation. Your sense of the past being fixed and the future being open, your ability to plan and anticipate, all of it depends on entropy increasing. Living in a universe where entropy decreased would not seem strange to you, because your memories would work in reverse, making the direction of decreasing entropy feel like the future. Time would still seem to flow from past to future, but past and future would be reversed from our perspective. Asking whether time could run backwards becomes a subtle question once you understand this. For any observer embedded in the universe, time always seems to run the right way. The psychological arrow aligns with the thermodynamic arrow automatically, because minds are physical systems that obey thermodynamics. A third arrow of time exists, the cosmological arrow. The universe is expanding, with distant galaxies moving away from us, and space between galaxy clusters growing larger each moment. This expansion has continued since the Big Bang, approximately 13.8 billion years ago. Gravitational attraction from all the matter in the universe slowed this expansion for most of cosmic history. But something remarkable emerged from observations about 5 billion years ago. The expansion started accelerating, pushed apart faster and faster by something we call dark energy. Naming it does not mean we understand it. Dark energy might be the cosmological constant Einstein introduced in 1917 and later called his greatest blunder, or it might be something stranger. The cosmological arrow, the direction of expansion, connects to the thermodynamic arrow in a subtle and beautiful way. An expanding universe gives gravity time to clump matter together, forming stars and galaxies, increasing entropy locally, while the overall expansion provides more room for that entropy to spread. Expansion gives the thermodynamic arrow time to operate. A static or contracting universe would behave very differently. I once wondered whether the thermodynamic arrow would reverse if the universe began contracting. If expansion stopped and everything started falling back together, would entropy decrease? Would broken cups reassemble? Would we remember the future instead of the past? For a time I thought the answer might be yes, that the arrow of time was tied to expansion. I was wrong again. Working through the physics more carefully revealed that entropy would continue increasing even in a contracting universe. The thermodynamic arrow would not reverse because boundary conditions matter more than direction of expansion. The special low entropy state at the Big Bang sets the arrow, not whether the universe grows or shrinks. Contraction would move toward higher entropy, not toward the ordered beginning. The collapse would end not in a pristine big crunch mirroring the Big Bang, but in hot, chaotic destruction. The deepest question remains: why were the initial conditions of the universe so special? Why did everything begin in such low entropy? Physics provides no explanation because the equations work equally well for any initial state, high entropy or low, with no preference. Most physicists accept the past hypothesis, but acceptance is not explanation. No theory derives it. James Hartle and I explored one approach at the University of California, Santa Barbara, involving the idea that the universe has no boundary in imaginary time. Picturing this is difficult, but imagine that tracing back toward the Big Bang changes time's character, making it become like another dimension of space. The universe would have no sharp edge, no moment of creation requiring explanation, just a smooth rounding off that completes itself. Asking what came before the Big Bang would be like asking what lies north of the North Pole. The question stops making sense because you have reached the end of that coordinate. If the Hartle-Hawking no-boundary proposal is correct, the boundary conditions are determined by requiring the universe to be self-consistent, to close in on itself smoothly. And remarkably, this requirement seems to imply that the universe must start smooth and low entropy. The special beginning would not be arbitrary, but a consequence of having no boundary. This remains speculation without definitive proof. The honest answer is that we do not know why the Big Bang was special. Not knowing, in physics, is where interesting work begins. Consider what this means for your existence. You are an entropy-increasing machine. Every breath, every thought, Every movement increases the entropy of the universe. You exist because the universe started in a low entropy state, providing a gradient for all the processes of life to run down. Without that special beginning, there would be no thermodynamic arrow. Without the thermodynamic arrow, there would be no memory, no experience of time passing, no you. The same principle operates everywhere. A business monopoly represents a low entropy state, highly ordered and improbable, maintained only through constant effort against competitive pressure. Standard Oil, the most powerful corporation in history at its peak, was broken apart in 1911. AT&T dominated telecommunications for decades before forced dissolution in 1984. The British East India Company ruled a subcontinent before dissolving into history. Competition increases economic entropy, spreading resources and power across many firms until equilibrium arrives. The same force mixing cream into coffee dismantled the largest corporations in history. Every CEO, every government, every empire fights the second law, and none of them win permanently. Ecosystems begin with few species and diversify until reaching dynamic balance. Civilizations rise from unlikely organization and gradually disperse their concentrated power. The arrow governing your coffee cup governs markets, ecosystems, and empires. Everything that exists fights a losing battle against equilibrium. Boltzmann himself worried about a strange consequence of his ideas, now called the Boltzmann brain paradox. Given enough time, random fluctuations will occasionally produce ordered structures purely by chance. Given infinite time, a brain complete with false memories could fluctuate into existence, believe it had a history, and dissolve back into chaos. Such brains would be overwhelmingly more likely than entire ordered universes. Why do we find ourselves in a vast cosmos rather than as isolated brains floating in chaos? This paradox has no solution, suggesting something remains missing from our understanding. The ultimate fate, if current understanding holds, is what physicists call heat death. Maximum entropy arrives, and nothing interesting can happen again. No stars, no planets, no life, no thought. Just a thin, cold, uniform sea of particles at the same temperature everywhere, stretched across distances so vast that particles will never interact with each other. This ending is not tragedy in the ordinary sense, but simply the logical endpoint of the second law, the final state of the cosmic puzzle. The direction of time is not fundamental. It emerges from boundary conditions, from the fact that the universe happened to begin in a particular way. Different beginnings would mean different everything. The arrow of time points where it does because of what happened 13.8 billion years ago. Every moment you experience, every memory you form, every second that seems to tick by traces back to the Big Bang. Coffee cooling in your cup connects to the first moments of the universe. The battery draining in your phone obeys the same laws governing burning stars. The arrow of time in your kitchen is the same arrow that emerged from primordial order. Watching ice melt or feeling yourself grow older means watching the universe evolve away from its special beginning. You are part of a process that has been unfolding since the origin of everything. The direction of time is cosmic, not small or local. It connects your breakfast table to the Big Bang. Something humbling lives in this understanding. We are not separate from the universe, but part of its thermodynamic unfolding. Our experience of time, our memories, our sense of past and future arise from cosmological boundary conditions set billions of years before Earth existed. Yet something remarkable emerges too. Out of increasing entropy, out of the cosmic clock running down, complexity has appeared. Stars have formed, planets have cooled, and life has evolved. Ilya Prigogine won the Nobel Prize in 1977 for showing how order emerges from chaos in systems far from equilibrium, how hurricanes and living cells and brains arise even as the universe slides toward disorder. But this order is local and temporary, purchased at the price of greater entropy elsewhere. Your existence increases the entropy of your surroundings. You are a brief eddy of organization in the river of dissolution. Boltzmann saw this clearly, perhaps too clearly. He understood that we exist in a fluctuation, a temporary structure of order, amid endless entropy increase. The fact that we can ask why time flows as it does is itself a consequence of that flow. We are the universe contemplating its own arrow. The direction of time is not a fundamental law written into reality, but an accident of origins, a boundary condition, a consequence of how things happen to begin. The universe did not have to be this way, and different beginnings would have meant different everything. But it started as it did, in pristine smoothness, and time has flowed in one direction ever since. Every moment you experience is a gift from the Big Bang. Every passing second carries the universe further from its special origin. Every memory you hold records entropy's increase, linking you directly to the first instant of creation. We remember yesterday and not tomorrow because of how the universe started. We grow old rather than young because of cosmological boundary conditions. The arrow of time is not a mystery physics alone can explain. It is a consequence of the initial state of the question of why the universe began as it did. That question, why those initial conditions, may be the deepest question of all. Perhaps the no-boundary proposal answers it, with the universe being self-contained and self-consistent. Perhaps new physics awaits discovery. Perhaps it is simply a brute fact, an unexplained given, the ultimate boundary condition on everything that exists. Whatever resolution eventually comes, the mystery of time's direction reveals something about our situation. We do not stand outside the universe looking in. We are part of it. The arrow of time governing your life is the same arrow governing the cosmos. Your experience of past and future is continuous with the expansion of galaxies and the burning of stars. No fundamental direction is written into the laws. Only this universe exists, with its particular beginning, evolving in its particular way. Time flows in that evolution. Cups break and do not unbreak. We remember yesterday. The cosmos runs down from improbable origin toward inevitable equilibrium. That is not tragedy. It is the condition making everything possible. Without the arrow of time, there would be no change, no growth, no life, no love, no discovery. The direction of time is the price of existence, and that price was set in the first fraction of a second, when the universe was smooth and hot and dense, before stars or planets or people existed to wonder why time moves as it does. Boltzmann paid his own price for understanding this too soon. Physics was not ready. He never lived to see Einstein validate the atomic theory underpinning his statistics, or Shannon prove that information and entropy are the same, or Bekenstein and me extend his insights to black holes. He died thinking he had failed. He was wrong about that too. The direction of time is the signature of the Big Bang, written into every process in the universe, including the neurons firing that allow you to understand these words. Past and future are not symmetric. They never were. They never could be. And now you know why.